Forget sharks, forget crocodiles, forget every apex predator you've ever seen on a nature documentary. There is a creature drifting through our oceans right now that has no brain, no heart, no bones, and no blood. And it was already ancient when the very first backbone evolved on this planet. It has outlived at least 4 mass extinctions, including the one that wiped out the dinosaurs. And it did it all without a single organ most animals consider essential for survival. This is the jellyfish, and almost everything you think you know about it is incomplete. And here's the twist we'll come back to before the end. One particular species of jellyfish appears to have found a loophole around death by old age itself. Biologists have watched it happen in laboratory tanks over and over. Stay with us, because the explanation is stranger and more limited than the headlines usually make it sound. Let's start with scale, because numbers alone don't do justice to how old jellyfish really are. The earliest fossil impressions that likely belong to jellyfish-like organisms date back more than 500 million years. Dinosaurs, by comparison, didn't show up until roughly 230 million years ago. If you compressed the entire history of complex ocean life into a single 12-month calendar, jellyfish would already be swimming around by early January. Dinosaurs wouldn't arrive until October. Modern humans would show up in the final seconds before midnight on December 31st. Jellyfish were pulsing through the sea before continents had drifted into the shapes we'd recognize on any map today. Across that unimaginable step of time, the planet went through at least 5 mass extinction events, each one wiping out somewhere between 70 and 90% of all species alive at the time. Jellyfish sailed through every single one. The reason sounds almost too simple. The fewer complex systems a body depends on, the fewer things there are to break when conditions change catastrophically. No lungs that need a precise gas mixture. No complex circulatory system sensitive to temperature swings. No energy-hungry brain to keep fed. A body built this efficiently just has less to lose when the world falls apart around it. But simple construction doesn't mean simple behavior. And that's where things get genuinely strange. A jellyfish has no brain in the sense we understand the word, no central command center like the one running the show in a human, a dog, or even an earthworm. Instead, it has what's called a nerve net, a diffuse web of nerve cells spread evenly across the body, with extra density around the rim of the bell. Picture a company with no CEO at all, just hundreds of equal employees who each react to whatever happens nearby. And somehow, without a single person giving orders, the whole company still moves in one coordinated direction. That's roughly how a jellyfish's body operates. No single self pulling the strings, just a distributed, cooperative response spread across the entire animal. And yet certain species, box jellyfish in particular, have actual eyes arranged around the rim of the bell, up to 24 of them. Some built with a lens, a cornea, and a retina, not far removed anatomically from our own eyes. A creature with no brain is carrying an organ that, structurally speaking, isn't so different from the one you're using to read this. Where the visual signal from those eyes actually goes, and how it gets processed without a central processor, remains an open question that keeps marine neuroscientists up at night. But that's not the only surprise hiding in the anatomy. Look at what a jellyfish is actually made of. In most species, 95 to 98% of the body is water. What's left, barely 2 to 5%, is a thin layer of cells, some connective tissue, and the bare minimum of structures needed to survive. If you evaporated all the water out of an average moon jellyfish, roughly the size of a dinner plate, you'd be left with a film just a few millimeters thick, weighing only a handful of grams. Humans, for comparison, are about 60% water, and even that number tends to surprise people who think of their own bodies as solid and dense. A jellyfish takes that idea to an extreme. It's essentially seawater that has organized itself into a shape capable of moving, feeding, and reproducing. There isn't a single bone anywhere in that body either. No spine, no shell, no internal skeleton of any kind.
Shape comes entirely from a hydrostatic skeleton, water pressure held in place by elastic tissue, the same basic principle that gives an inflatable mattress its form. That's exactly why a jellyfish stranded on a beach collapses so quickly. Without the surrounding water to support that internal pressure, and without any rigid structure of its own, the body simply deflates into a puddle of jelly within hours. But its most famous weapon is still ahead of us. A jellyfish doesn't hunt the way we usually picture predators hunting. It doesn't chase, doesn't ambush, doesn't sprint after prey. Instead, it relies on one of the most efficient offensive tools evolution has ever produced: stinging cells called cnidocytes. Millions of microscopic capsules line the tentacles, each one holding a coiled thread lined with tiny barbs. At the slightest mechanical or chemical trigger, the capsule fires. The thread shoots outward with an acceleration that, relative to its size, ranks among the fastest processes documented anywhere in the living world, dramatically faster than a car airbag deploying in a crash. The entire event takes a fraction of a millisecond, faster than any reflex a human body could ever manage. The venom delivered through that thread varies enormously between species. Some cause nothing worse than a mild rash comparable to a bee sting, while others can stop a human heart within minutes. It's the venom, not size or teeth, that makes certain jellyfish some of the most dangerous animals in the ocean. And we'll get into the real, documented cases behind that reputation shortly, because some of them are genuinely unsettling. Most people don't realize this, but if you never subscribe, YouTube may eventually stop recommending our videos to you. Hit subscribe now so you don't miss future uploads. If you enjoy the video, a like or comment really helps too. Movement is just as unusual. There are no fins, no limbs, no muscles in the conventional sense, just a ring of muscle fibers around the bell that contract rhythmically, pushing water out from underneath like a bellows and creating jet propulsion. In a very real sense, jellyfish were among the first organisms on the planet to master jet propulsion, doing it hundreds of millions of years before humans invented an engine running on the exact same principle. That said, most jellyfish are fairly poor swimmers compared to fish or squid, and rely heavily on ocean currents to travel any real distance. The jet is mostly used for local adjustments, rising toward the surface, dodging a threat, correcting depth. There's another trick some jellyfish carry that has nothing to do with hunting or defense at all: light. A number of deep water and open ocean species can produce their own glow through bioluminescence, and one particular species, Aquaria victoria, a small, unassuming jellyfish found off the Pacific coast of North America, ended up changing modern medicine almost by accident. Researchers studying its glow isolated a molecule now known as green fluorescent protein, or GFP, which lights up bright green under blue light. That discovery eventually earned a Nobel Prize because scientists realized they could attach GFP to virtually any gene in any organism and use the glow as a built-in tracking light, watching in real time exactly when and where a gene switches on inside a living cell. Today, GFP derived from that one jellyfish species is used constantly in cancer research, neuroscience, and genetics labs around the world.
illuminating everything from tumor growth to nerve activity. It's a strange thought. Some of the most important tools in modern biology trace back to a brainless, drifting animal nobody thought twice about until the 1960s. And it's worth pausing here to clear up one of the most common points of confusion in this entire topic. The Portuguese man-o'-war, the creature with the distinctive blue, balloon-like float and trailing tentacles that can stretch tens of meters, is routinely called a jellyfish. But technically, it isn't one at all. It's a siphonophore, not a single animal, but a colony of many specialized, genetically identical organisms, each one unable to survive independently, functioning together as though they were one creature.
Some of those organisms form the gas-filled float. Others handle stinging and capturing prey. Others digest food. Others reproduce. An entire division of labor spread across what looks, from a distance, like a single jellyfish bobbing on the surface. Even after washing ashore and drying out, a man-o'-war's tentacles can still deliver a painful sting, which is why beaches occasionally close after a mass stranding, even though, technically, no true jellyfish is involved at all. And here's where the story gets genuinely bizarre: the life cycle. Most people picture a jellyfish as one continuous creature. Born a jellyfish, lives its whole life as a jellyfish, dies a jellyfish. The reality is far stranger. Most true jellyfish species pass through two completely different life stages that look, for all practical purposes, like two different animals. A fertilized egg develops into a tiny swimming larva, which quickly settles onto a hard surface, a rock, a shell, the sea floor, and transforms into a polyp, a stationary, anemone-like organism anchored in place. In this form, the organism can spend months or even years simply feeding and reproducing asexually, budding off identical copies of itself. Then, when conditions align, the right water temperature, the right light levels, a shift in water chemistry, the polyp begins a process called strobilation. Its body divides into horizontal segments, stacked like a pile of plates, and each disc peels away and swims off as a fully formed, if tiny, jellyfish. A single polyp can release dozens of jellyfish in one cycle. Imagine a person freezing in place for years at a stretch, then suddenly releasing dozens of fully grown copies of themselves that swim off to live independent lives. That's roughly what this looks like from the outside. But we haven't gotten to the strangest part yet. There's a species barely the size of a fingernail, native to the Mediterranean and now spread across much of the world's oceans. Turritopsis dohrnii, nicknamed in popular media the immortal jellyfish. When injured, starved, stressed by temperature swings, or simply aging, this animal can reverse its own development. Its adult cells don't die off. Instead, they transform back into polyp cells, and the entire organism physically reverts to an earlier stage of its life cycle, essentially starting over. Picture an adult human under extreme stress, literally reverting to infancy and growing up all over again, retaining some of the original material but without conventional aging. That reversal is exactly what earned this species the label biologically immortal. It doesn't mean the jellyfish can't be killed. It dies easily enough if eaten by a predator, caught by disease, or dropped into hostile conditions. What immortality means here is narrower. There's no programmed aging process leading to death from old age. As long as external circumstances allow it, the cycle can theoretically repeat indefinitely, resetting the clock instead of running it down. Researchers studying this reversal treat it as a potential window into cellular aging in general,
Not because humans are headed toward anything similar anytime soon, but because the biological switches involved might reveal mechanisms that exist, in some dormant form, in far more complex animals too. It's also worth pointing out just how varied this group of animals actually is, because jellyfish isn't really one thing. There's the upside-down jellyfish, which spends most of its life lying bell down on shallow sandy seafloors, tentacles pointed toward the sun like a plant, hosting the same photosynthetic algae that live inside corals, and effectively farming sunlight for food instead of hunting. There's the crown jellyfish, ringed with a distinct groove around its bell, like a satin-shaped crown, drifting in deep water, far below where sunlight reaches. There's the blanket octopus, unrelated to jellyfish entirely, but famous for tearing off man-o'-war tentacles and wielding them as weapons, which shows just how deeply the influence of stinging cells reaches across ocean ecosystems, even among animals that aren't jellyfish at all. Somewhere between 2,000 and 4,000 species of true jellyfish and related gelatinous animals have been described so far, and researchers strongly suspect many more remain undiscovered in deep water that humans have barely explored. That same simple muscle ring propulsion system has caught the attention of engineers far outside marine biology. Several robotics labs, including research funded by aerospace agencies interested in long-duration ocean monitoring, have built soft, jellyfish-inspired robots that mimic that rhythmic bell contraction instead of relying on a rigid propeller. The appeal is efficiency and durability. A soft, flexible, pulsing body has fewer moving parts to break down during months of continuous underwater operation than a conventional propeller-driven vehicle, and it disturbs surrounding marine life far less. In other words, an animal with no brain at all has become a genuine engineering blueprint for machines meant to quietly patrol the ocean for years at a time. Let's come back down from the biology of immortality to something a little more grounded, where jellyfish actually fit in the ocean's food web. Despite the venom, jellyfish are nowhere near the top of the food chain, and they're far from invulnerable to predators. Sea turtles, especially leatherbacks, essentially specialize in eating jellyfish, sometimes consuming dozens of kilograms of jelly in a single day. Because jellyfish are low in calories, and a turtle needs to eat an enormous volume to get enough energy. Ocean sunfish, among the heaviest bony fish on the planet, feed heavily on jellyfish and related organisms too. Certain tuna species, albatrosses, and even some sharks include jellyfish in their diet, especially during blooms, when jellyfish become so abundant that they're simply easier to gather than more energy-dense prey. In some coastal food webs, jellyfish blooms even provide a seasonal buffet substantial enough to influence the migration timing of the predators that specialize in eating them, with tracked leatherback turtles altering their routes year to year to intercept dense patches of jellyfish drifting along ocean currents. There's a darker side connected to human activity here too. Floating plastic bags, in shape, translucency, and motion, look remarkably like jellyfish drifting in open water, and sea turtles regularly mistake them for food. A swallowed bag can block the digestive tract entirely, leaving the turtle unable to feed properly, and it often starves to death with a stomach that's technically full. Researchers examining the stomach contents of deceased sea turtles have documented exactly this pattern repeatedly: plastic where jellyfish should have been. But jellyfish aren't only prey, they're also active participants in genuine symbiotic relationships. Certain small fish, particularly juvenile jacks and a handful of other species, live literally inside the bell of a jellyfish or hover in close proximity to its tentacles, using the host's stinging cells as protection from larger predators. The fish itself carries partial resistance to that specific jellyfish's venom and sometimes returns the favor by picking off parasites from the bell. It's a textbook case of commensalism, occasionally tipping into mutualism, playing out constantly in open water. The passenger gets protection, and the host sometimes gets a small benefit in return. Researchers explain the fish's resistance in a less magical way than you might expect. It isn't full immunity. It's a thick, protective mucus coating that physically blocks the stinging threads from penetrating the skin. More like a thick wetsuit against thorns than any kind of biological shield. Since we're already on the subject of stings and venom, this is the right moment to get into the question most people actually clicked for. How dangerous are jellyfish to humans? Really? Dry statistics alone won't capture it, so a few real documented cases are worth walking through. Start with a species toxicologists frequently rank among the most dangerous animals in any ocean anywhere. The box jellyfish, found mainly in warm waters across the Indo-Pacific, off the coast of northern Australia and throughout Southeast Asia. Unlike the slow, drifting jellyfish most people picture, box jellyfish can actively and fairly quickly propel themselves through the water, using those camera-like eyes to navigate around obstacles. They genuinely see where they're going, which is rare for a jellyfish.
The venom carried by some box jellyfish species attacks the heart, the nervous system, and skin cells at the point of contact simultaneously. With extensive tentacle contact, and tentacles on some species stretch up to 3 meters, the dose delivered can be enough to stop a human heart within minutes, often before the person even makes it back to shore. Lifeguard services along northern Australia's coastline post seasonal warning signs on beaches and keep anti-venom stocked specifically because of this species. Researchers tracking regional marine incident statistics have documented cases over the years where swimming in calm, warm, perfectly clear water turned fatal within minutes, before anyone fully understood what had happened. It's that speed, not any particular cruelty in nature, that makes the box jellyfish such a compelling subject for documentaries. The danger arrives with no warning, no visible predator, no sound at all. But that's not even the most deceptive part of the story. Along that same stretch of Australian coastline lives another species, far smaller, sometimes no bigger than a sugar cube, merely invisible in open water, responsible for a condition with its own medical name, Irukandji syndrome. Unlike a box jellyfish sting, an Irukandji sting can feel almost harmless at first, often compared to a mild nettle burn. But 20 to 40 minutes later, an entirely different picture emerges. Severe lower back pain, chest and abdominal pain, nausea, a genuine sense of impending doom, and spikes in blood pressure. Emergency doctors in regions where this jellyfish appears regularly are specifically trained to recognize the syndrome, precisely because of that delayed onset. Patients often leave the water, get dressed, and drive home before realizing something is seriously wrong. According to lifeguards and clinicians working along that coast, Irukandji syndrome sends dozens to hundreds of people to emergency care every year in affected regions, though fatalities remain relatively rare thanks to modern emergency treatment. Still, the fact that a jellyfish the size of a fingernail can put a healthy adult into intensive care says everything about how little venom potency has to do with the size of the animal producing it. Researchers explain this fairly simply. The quantity of venom matters far less than its biochemical precision. A tiny dose that hits exactly the right receptors in the nervous or cardiovascular system can outperform a much larger volume of something less specific. Nature, in this case, is economical rather than wasteful.
Why manufacture large amounts of venom when a small, precisely engineered dose gets the job done? Accounts collected from hospital staff in affected coastal towns describe a fairly consistent pattern among Irukandji patients. A swimmer gets out of the water feeling fine, sometimes even laughs off the initial sting as barely noticeable, then, within half an hour, is doubled over in an emergency room, gripped by chest pain and an overwhelming sense that something is terribly wrong, before treatment brings the worst of it under control over the following hours. Multiply that pattern across a single bad season, and it's easy to see why some beach towns in the affected regions see real, measurable dips in summer tourism whenever local health authorities issue public warnings. An economic ripple effect from an animal most visitors never even see coming. There's a less tragic but equally telling category of incidents: mass jellyfish invasions colliding with human infrastructure. By various accounts from engineers and coastal authorities, jellyfish swarms have repeatedly clogged the seawater intake systems of coastal nuclear power plants in multiple countries, from Japan to Israel to Scotland, forcing operators to temporarily shut down or throttle reactors until the intakes could be cleared of jelly. In one especially striking case, reported in Defense Trade Press, a United States aircraft carrier operating in East Asian waters had its cooling water intakes clogged so severely by a jellyfish swarm that crew members had to manually clear the filters over several days. A multi-billion-dollar warship, loaded with cutting-edge sensors and weaponry, temporarily hobbled by an animal with no brain at all. Fishing fleets in parts of Southeast Asia and Japan face a related problem with Nomura's jellyfish, whose bell can reach 2 meters across and weigh as much as 200 kilograms. Swarms of them tear fishing nets apart under their own weight and fill ship holds with jelly instead of catch, causing real economic losses that, by various estimates, run into the millions of dollars in particularly bad seasons. There's an even more dramatic account from the late 1990s, when a massive swarm of jellyfish was reported to have been drawn into the cooling water intakes of a large power plant in the Philippines, contributing to a widespread blackout that left millions of people in the capital region without electricity. As with most large-scale power failures, several factors were likely involved at once, but eyewitness accounts and utility workers at the time pointed to jelly-clogged intake screens as one clear trigger that night. A striking reminder that an animal without a single neuron organized into anything resembling a brain can, under the right circumstances, briefly outmaneuver an entire national power grid. Not every human relationship with jellyfish ends in an emergency room, though. In several East and Southeast Asian culinary traditions, certain species, including that same enormous Nomura's jellyfish causing headaches for fishing fleets, are deliberately harvested, processed, and eaten. The process is surprisingly involved. Fresh jellyfish are treated with a mixture of salt and alum over several weeks, which draws out water and firms up the tissue into something with a crunchy, almost cartilage-like texture, since raw jellyfish, left untreated, would simply dissolve into liquid within days. The finished product, usually thinly sliced and dressed with sesame oil, vinegar, or chili, is prized less for flavor, which is fairly mild, and more for texture. Global demand has actually turned jellyfish harvesting into a genuine industry worth hundreds of millions of dollars a year. And some researchers have floated the idea, only half-jokingly, that the best long-term solution to exploding jellyfish blooms might simply be a bigger dinner plate, more fishing pressure aimed at jellyfish themselves instead of their competitors. Speaking of 200-kilogram jellyfish, this is a good moment to talk about records, because the world of jellyfish is full of extremes that challenge how most people picture these animals. The longest jellyfish on the planet is the lion's mane jellyfish, found in the cold waters of the northern Atlantic and Pacific. The bell of a large specimen can exceed 2 meters across, and its tentacles can stretch beyond 30 meters. For comparison, an adult blue whale, the largest animal ever to exist on Earth, measures roughly 30 meters long. A creature with no bones, no brain, and a body that's almost entirely water can physically outstretch the biggest animal in the planet's entire history. The smallest true jellyfish, by contrast, are so tiny their bells are comparable in size to a grain of rice, essentially invisible to the naked eye in open water, which, as the Irukandji story already showed, can itself become a source of real danger, precisely because it's so hard to see coming.
The longest-lived stage isn't the adult jellyfish at all. It's the polyp, which can persist for decades in some species, quietly producing new generations of jellyfish year after year, while the free-swimming adult jellyfish of most species lives only a few weeks to about a year. It's an odd reversal. The stationary stage of life can outlast the active stage by decades, which runs completely opposite to how life works for almost every animal we're familiar with. And of course, the strangest entry on this list of records is the immortal Turritopsis dornii we already met, theoretically capable of dodging death by aging indefinitely, while remaining one of the smallest, most easily overlooked creatures in the sea. One more record worth mentioning: reproduction speed. Under good conditions, a single polyp colony can bud off new jellyfish fast enough that a modest starting population can multiply into the millions within a single season, which is exactly the mechanism behind the sudden, overwhelming blooms that show up in beach warnings and news reports, seemingly out of nowhere. There's no gradual build-up you can watch coming. Conditions align, and what was an empty stretch of coastline a few weeks earlier is suddenly thick with jellyfish from shore to horizon. So let's return to the question we opened with. Is a jellyfish really immortal? And could you, in theory, encounter the very same individual again centuries from now? The answer is yes and no at once. The reversal mechanism genuinely lets individual cells sidestep typical cellular aging. And in theory, the cycle of jellyfish, polyp, jellyfish could repeat forever. In practice, though, the overwhelming majority of these jellyfish die long before ever using that ability. Eaten, caught in the wrong conditions, killed by pollution, or simple physical damage. Immortality here isn't a guarantee of eternal life. It's the absence of one specific cause of death, aging, while every other cause of death still applies at full force. Which brings us to a topic no modern conversation about jellyfish can avoid: human activity and its effect on jellyfish populations worldwide. Independent observations across many regions suggest that over the past several decades, the frequency and scale of so-called jellyfish blooms, sudden population explosions, have noticeably increased in a number of waters, from the Mediterranean to the Sea of Japan. Several intertwined causes seem to be driving this. Overfishing removes natural competitors for the plankton that both jellyfish and small forage fish rely on, effectively clearing the table for jellyfish once fish numbers drop. Warming coastal waters create more favorable breeding conditions for polyps of several species that prefer higher temperatures. And artificial structures, pier pilings, oil platforms, harbor infrastructure, shipwrecks, provide an enormous amount of new hard surface area, ideal for polyps to settle and grow in places where none previously existed. Add nutrient runoff from agricultural land draining into coastal waters, which fuels plankton blooms and, in turn, jellyfish blooms,
while simultaneously lowering oxygen levels to points uncomfortable for many fish, but perfectly tolerable for far hardier jellyfish.
The result is something close to a feedback loop, in which nearly every human activity connected to the ocean, fishing, coastal construction, climate change, agricultural runoff, ends up favoring jellyfish, which, unlike many other marine species, turn out to be remarkably well suited to surviving exactly the kind of changes humans are introducing to the sea. Researchers studying this phenomenon sometimes use the phrase jellification of the oceans, describing a gradual shift in certain ecosystems away from fish dominance and toward jellyfish and related gelatinous organisms. And it's worth remembering how much of this world remains genuinely unexplored. Remotely operated deep-sea vehicles occasionally capture footage of jellyfish species that scientists have almost never seen before, drifting thousands of meters down in total darkness, ghostly, sometimes enormous animals with bells the size of a beach ball and tentacles trailing far longer than the camera's lights can even illuminate. Some of these deep water species have only been recorded on video a handful of times in history, never formally collected, existing for science mostly as a few minutes of grainy footage and a rough size estimate. Given how little of the deep ocean has actually been surveyed, researchers generally assume there are jellyfish species alive right now that no human has ever laid eyes on. There's also a contrast worth drawing with coral, another ancient group of ocean animals that's structurally related to jellyfish in the broader sense. Both belong to the same wider animal group built around stinging cells. Corals depend on a fragile partnership with microscopic algae living inside their tissue, and even a small rise in water temperature can break that partnership apart, triggering the widespread bleaching events that have devastated reef systems around the world in recent decades. Jellyfish, by contrast, carry almost none of that fragility. Warmer water doesn't threaten their basic survival the way it threatens coral. In many cases, it simply speeds up their reproduction. Two animals built on the same ancient evolutionary chassis are heading in almost opposite directions as the ocean changes, one crumbling, the other thriving. And that contrast alone tells you a great deal about which body plans nature rewards when conditions shift quickly. There's a subtler pathway for jellyfish spreading around the globe too: ballast water carried by cargo ships. Massive tankers and container ships take on seawater for stability in one port and discharge it in another, often on the opposite side of the planet. Microscopic jellyfish larvae and even whole polyps clinging to the inside walls of ballast tanks travel along for the ride. That's how species that would never naturally cross paths, say a jellyfish native to one enclosed sea and the ecosystem of a coastline thousands of miles away, end up introduced into an entirely new environment, where local species may have no evolved defense against the new competitor. In a handful of documented cases, this kind of accidental introduction has been linked to sharp collapses in local fisheries, reshaping populations of small fish and shrimp in enclosed marine basins where the invasive jellyfish took hold. Even in death, jellyfish keep doing something quietly important for the ocean. When a large bloom dies off, huge amounts of jelly sink to the sea floor in what researchers have started calling jelly falls, sudden deposits of organic material dropping into deep water far below the sunlit surface. For scavengers and bacteria living on the deep sea floor, where food is normally scarce and every calorie matters, a jelly fall can represent an enormous, if short-lived, banquet. Some scientists studying deep ocean carbon cycles now treat jellyfish blooms as a genuine, measurable pathway for moving carbon out of the surface ocean and locking it away in deep sediment, alongside more traditional processes involving plankton and fish waste. An animal built almost entirely of water
turns out to play a real role in how the planet manages its carbon, simply by living, blooming, and eventually sinking in enormous numbers. Which brings us to the final, unexpected turn in this whole story. For a long time, jellyfish were treated as a kind of biological afterthought. Primitive, secondary creatures barely worth serious scientific attention next to more advanced fish, mammals, and cephalopods.
That view is changing fast.
Jellyfish aren't a minor side note in ocean ecosystems. They're one of the oldest and, at the same time, one of the most resilient mechanisms the ocean has ever produced, capable of absorbing almost any disruption humans introduce into the sea. In a strange way, a jellyfish isn't an anomaly in a healthy ocean. It's an indicator of what's actually happening to that ocean. The more jellyfish show up where fish used to dominate, the clearer the signal that the balance of that ecosystem is shifting, and not in our favor. Maybe the real irony is this: a creature with no brain, no heart, and a body that's almost entirely water might end up being one of the very few organisms that genuinely outlasts us. Not because it's stronger, but because it's built so simply and so efficiently that there's almost nothing left inside it to break when everything else falls apart.
500 million years from now, long after our own species has left whatever mark it's going to leave, there's a real chance that something very close to a jellyfish will still be pulsing quietly through whatever's left of the ocean, exactly as it has been doing since long before the first tree took root on land. If this video changed the way you look at jellyfish, hit like and subscribe, and let us know in the comments which sea creature we should cover next.